topic that I am very passionate about. I spent a lot of time thinking about APIs. I spent a lot of time thinking about long-lived and evolvable systems. And I think this is an interesting challenge to start to overcome. And I don't believe necessarily the solution to the challenges we have around evolvability and extensibility and adaptability of APIs and distributed systems that we're trying to integrate together, I don't know if it necessarily can be solved purely by throwing technology at the problem. Although there are a lot of very cool and interesting technologies that are great tools and stepping stones towards moving to a more long-lived thing. So, of course, the customary introductions, you've probably heard me say this a couple times today, that I live somewhere at the intersection between magic and technology. And in a lot of ways, the magic that I'm very interested in these days surrounds turning information into knowledge and data into information, information into knowledge. And I'm an independent consultant. I help my clients with knowledge management and the architecture and implementation of knowledge systems. I do a lot of research and development in the knowledge graph space. And what's been really interesting being in that space is how your API strategy really enables cross-domain connected systems, cross-domain insights, being able to break down silos, things like that. And so as a result of that, I spent a lot of time thinking about APIs, evolvability, solving long-term problems, and what become long-lived software architectures. Now, this is a vaguely titled talk, and a little bit of this is by design, a little bit of this is on purpose. But I think it might be worth going back for a moment and setting some definitions, right? What do we mean by flexible? What makes an API flexible? We had a lot of conversations about architecture today, and Mark Richards gave a wonderful opening keynote that was followed by an equally wonderful session by Neil Ford, and it's just been a great day all day. So if we're going to define this flexibility thing, what this is, I think it can be useful to define it in the context of architectural characteristics, what Mark called architectural ilities. So ilities for flexibility. Flexibility is an ility, but how do we break this down? I mean, these are things like evolvability. We think an API is flexible when our needs change and we want our API to adapt. We want to be able to evolve into these new needs. Extensibility. Can we use this in ways that we didn't originally anticipate? Adaptability. Adaptability, extensibility, there's a lot of similarity and overlap there. Composability. That's a really cool capability that we get out of certain approaches to APIs, that we can take pieces of the API and put them together and get new things. If you think about this idea of composability, it's central to almost every aspect of engineering. We put two things together and we get something new that has characteristics beyond what the two component pieces have. Scalability is another area where we need flexibility. It's flexible. It'll work well when the demand is small, but will it be flexible enough to grow and scale as our needs change? Portability, interoperability, localizability, compatibility. These are all ilities that really kind of fall under this umbrella of flexible. And so there's a lot that comes into just that word. What about smart? What does that mean? Well, I think we can come up with a couple ilities that can really capture the essence of what we're trying to communicate here with smart. Things like securability, testability. APIs can be historically difficult to test, but there are approaches that might make that a little more testable. Understandability. How much do you have to know to start working with this API and start getting from benefits of it? Tooling surrounding the API, observability, efficiency, configurability. All of these seem to fall under the umbrella of smart. And what about self-describing? Well, part of that comes just from being standards compliant, that we know what to expect when we interact with an API. We can have self-documenting endpoints. We can even have self-documenting data, and self-documenting data in really amazing ways. But a really key one that we almost never see in APIs, but we're starting to because the value is starting to emerge from this, is application-independent semantics. So in other words, if I want to go and consume, let's say I work in an enterprise and we've got a bunch of silos all over the place, and the business comes to you and you have a need that you need to get some data out of this silo, some data out of this silo, some data out of that silo, integrate it all together, project it into a new projection that's going to answer a certain business question. Well, there's a whole lot beyond that data. There are all these semantics. There's all this implied meaning and behavior of the data that doesn't live with the data typically. That lives in application code. And so if I want that, I'm either going to have to read the code or read a lot of documentation to understand what the business rules are. That this is a social security number, which means it has this specific format and there can be only one. Or this is a phone number and it has that specific format and these specific constraints. And you can have up to 3 or whatever this is. Or this references that. This term, this one term, like the term title, means specifically some kind of title. Because when we just look at the name value pairs in JSON, if I have a name value pair and the name of that property is title, what does that mean? It could mean a lot of things, right? It could be the title of a book. It could be the title that you address somebody. It could be an honorific. It could be nobility. It could be the title of a document. There's so many different, there's so many different semantics overloaded in one word. And all of that exists somewhere, usually in code, but a truly self-describing API allows all of that meaning and metadata to go with the data. So when you pull that data out of that silo, you have all of it. You don't have to hand code and recreate all of those semantics and all of those constraints and all of those business rules. And that's a really interesting dimension of self-describing that is possible, but we very rarely see it. So we talk about these three things. Smart, flexible, smart, self-describing. All of these sound like really desirable things. So we need to build this into all the APIs that we ever build, right? Well, to quote Mark Richards, it depends. The universal answer to every software architecture question. This is why I like being a software architect, because nobody can ever corner you with a difficult question. Well, have you thought about that? Well, yeah, of course, and it depends. I mean, there are a number of factors. I don't know if we have time to discuss them all right now, but it's a very good out. And you always sound smart, too. You're like, well, because you're thinking, you're reasoning. So APIs are really not just code, they're a core part of our architecture. They're what connects distributed systems. They're the interfaces that we can plug other applications into. And so the decisions we make, these are architecture decisions. Well, where do good architectural decisions come from? Well, sometimes they're made based on what's trending, right? Buzzword-driven development. Other times architecture decisions come from what would look good on my resume. We have the resume-driven development, because we all want microservices on our resume because that seems to be what everybody wants. And usually we're looking for people with microservices on their resume because there are people in the company that are trying to hire you that want microservices on their resume, but they realize they need somebody who knows how to do this, so they're looking for you so they can join the club. Yes, that's how it goes sometimes. Or solution space development. I've talked about this a few times. This is where we're constrained by what we already know how to do rather than looking at the problem that needs to be solved. It's where we look at something and say, well, this is what I know how to do, or this is what I usually do, therefore that's how I'm going to solve this problem. It's like the golden hammer. When the only tool you have is a hammer, every problem starts to look like a nail. Some architecture decisions get made by indecision, but literally not making a decision is a decision. And it's a decision in itself. In these cases, we tend to get what's called an accidental architecture. So if we're not just looking at what Google's doing or what Netflix is doing or what's trending on Hacker News or what has the most stars on GitHub, then where do these decisions come from? Well, let me give you an example. For better or for worse, I work in the technology industry. That means to my family, I am the go-to tech support person. Even though, like, all I'm going to do is Google their question. That's all I'm going to do. And I'll even do it in front of them. I don't know. Let's type in the thing you're trying to figure out how to do. Well, there's the answer. Oh, you want me to do all the clicking for you? Sure, why not? By the way, I should tell my parents I have an hourly rate. I want to see what happens, or my grandparents especially. But if you're in this industry, inevitably the same thing is going to happen to you. So let's say you've got your older grandmother or an older family member, knowing that you work in the computer industry, that you work with computers. They want a recommendation. Well, what computer should I buy? Now, me personally, I have a pretty good idea of what I would consider to be a great computer. If you said, what kind of computer should I buy? My default is what kind of computer that I want instead of what computer you should buy. But it really depends on what they want to do with it. So I'd ask Grandma, I'd say, well, what do you actually want to do with this computer? Well, it turns out Grandma mostly wants to use this computer to browse the web, read email, and look at funny pictures and videos of cats. Well, any computer that you buy today can pretty much handle that. I mean, a Raspberry Pi could do that. But so could the really expensive computer that I would spec out. The $7,000 powerhouse. Because faster is always better, right? More memory is always better. Because definitely Grandma needs that 4090 Ti and 128 gigs of DDR, 5 now, RAM? The 7800? Or whatever the fastest it is now. She needs a 13th gen Core i9, liquid cooled because we're going to overclock it to 5.5 gigahertz. And I lay all this out to my grandmother, and she says, oh, I wasn't planning on spending $7,000 on a computer. And this is great because I'm losing my voice. It's really easy to do my grandma voice. But she didn't want to spend $7,000 on a computer. Oh. I guess cost is a factor, and that falls into another category of requirements. These are the non-functional requirements. You know, I actually don't like to call them non-functional requirements anymore because I would go into companies and be like, well, let's talk about the non-functional requirements. And their reaction is, oh, we don't care about the non-functional requirements. We care about the features that our customers are going to use. Yes, but your customers actually want to be able to use these features, right? Then let's make sure that it does everything else to allow your customer to use those features. So sometimes you call them system qualities or abilities or architectural characteristics. But if we look at this, well, those are mine, right? Performance, portability, scalability, upgradability, extensibility, customizability, ... Well, that's what matters to me, so it must be what matters to them, right? Oh, I guess not. There's cost and simplicity. And good architectural decisions work exactly the same way. And it's easy to look at both of these two options and reductively proclaim that the faster or the trendier technology is always better. The truth is, there are an almost infinite number of ways to configure a personal computer to satisfy basic functional requirements, just like there's almost an infinite number of ways that we can write code that will satisfy a set of functional requirements. And architects define the constraints that developers have to work with to satisfy both. And it's really important that we get this right. I'm going to quote Mark Richards again. If you don't have the right architecture in place, or you choose the wrong architecture for a given project, generally the functionality will work, but the application as a whole won't be a success. And you've heard this so many times today. There are no best practices. There are only trade-offs. But let's look at another example. This is a recent generation of iMac. What a beautiful computer. It is amazing. I've watched the evolution of the iMac since it was introduced. I've owned Apple computers since the 80s, although I stopped somewhere in the late 20-teens for some reason. And, when I look at this, though, it just seems like the pinnacle, the peak of design. Now, the folks at Apple, they selected a core non-functional requirement of this very slim form factor. And they succeeded. Literally every component of that system is in that tiny display. It's powerful. It's flexible. It's a truly a triumph of engineering. It's a thing of beauty. Now, that kind of engineering, it might cost a little bit more, which is fine, but there are much bigger consequences to this decision. Fundamentally, it's a design trade-off. To achieve this particular trade-off, that particular non-functional requirement, other ilities had to be sacrificed. Nothing is ever for free. So they chose an integrated architecture over a modular architecture. That means that on the one hand, you get the very slim form factor. On the other hand, once it's built, you can't change it. If you buy that machine, to get that design, it required a sacrifice, a trade-off of a bunch of other ilities. Modularity, extensibility, upgradability, modifiability, customizability, evolvability, agility, portability. That's a lot of trade-offs. Now, it also means that when you buy that iMac, you'd better get the right one. Because if you get the 16 gig model and you wish you had gotten the 32 gig model, well, you got to buy a new machine. It's soldered onto the motherboard. These aren't DIMMs you could just swap in and out. It means that if you got the 512 gig hard drive and you wish you had the 2 terabyte, well, you have to buy a new machine. If you got the 24 inch and you wish you'd got the 32 inch or 29 or whatever the sizes are, you have to buy a brand new machine. Now contrast that with the modular style tower PC. Now, I've got a machine, this isn't what I have, but I've got a machine that's kind of like that. It's bigger, it's bulkier, but all of the components can be swapped out. The computer that I have at home right now, I've customized the case twice. I've replaced, I've upgraded the memory a couple of times, I've upgraded the graphics card, I've upgraded the processor, I've upgraded the storage, I've upgraded the motherboard. Come to think of it, I've rebuilt this machine over a period of time. This is the computer version of the ship of Theseus. But I've done all of these things, and it's bigger, it uses more power. I've upgraded the cooling system a couple of times too. But this trade-off makes the computer more evolvable and upgradable and extensible and adaptable and customizable and modifiable and scalable. But again, it comes at a cost. It's much bigger. It consumes a lot more power. It's a lot noisier. But these are all deliberate choices, and this is the key. Architecture is about making deliberate choices. So if the form factor matters most, then buy an iMac. If the qualities of upgradability and evolvability, et cetera, then buy a Mac Pro or a tower-style PC. And the same is true of software projects. When you make one ility stronger, we must make other ilities weaker. And there are always trade-offs, and this is why knowing what matters most in a project allows us to drive these decisions. So if you're building an API, the first question you should ask is, who is your consumer? And the second question you have to ask is, what kind of experience do you want to give them? And these are really, really important questions. And a lot of times, when we initially build an API, we're just thinking about a back end for our web front end or something like that. And one of the questions I always ask is, well, would your business benefit from more than this? Or is it something you might benefit from in the future? Because if all you're building is a tightly coupled back end for your front end, then a lot of this doesn't really matter because you control the life cycle of the client and the server. And your organization is probably small enough that you can coordinate across those boundaries. You can rely on a lot of out-of-band information. But it's going to be different if later you say, you know what, we really want to make this public. And I'm going to tell you a secret. As soon as you build a back end for your front end, and you make the mistake of calling it an API in front of a business person, then they're going to be talking to a customer in a couple of weeks. Well, does your application have an API? Oh, yeah, we definitely have an API. And it's the ad hoc API that you threw together, for your limited set of needs, and all of a sudden, now it's public. And people are judging your API, and wow, there's no consistent style, and there's no consistent conventions and things like that. So let's talk a little bit about APIs, how they evolved, and what we want to get from them. and how we can do this, and how different approaches give us different strengths and weaknesses, different trade-offs. And approaching it from that direction, that really helps you make these architecture decisions and navigate these architecture trade-offs. So if we go all the way back to the early days of writing code, once we got to a certain level of abstraction with code, like I remember when code was just a big, long list of instructions. We had no modules, we had no methods, we had no classes. Just one after another. Oh, you need branching? Go to. Go to. The only thing worse than go to, by the way, was somebody as a joke, they tried to think of something worse than go to. Have you heard of this? And so they came up with a specification for something called come from. So let's say you've got line 40 where you'd have, let's say line 40 of your basic program, you'd say go to line 100. Well, as you're reading it, you're like, okay, go to 100. But the way it would work is on line 100, it would say come from 40. And so you'd read 1, 2, it was like a magic trapdoor in your code that you didn't know was there until all of a sudden, now you're way over there. But we outgrew that, and once our programming reached a certain level of abstraction, we could organize things in the modules. We could divide our codes into methods and modules and things like that, and it allowed us to structure our code for better reusability, modularity, maintainability, and understandability. And that also meant, but it was all in the same package. It was all in the same application. We didn't really have distributed systems yet, at least not very often. And so that meant that if I wanted to call a method in a different module, I would just do so. And all of these modules were linked at compile time, so it wasn't that big of a deal. Now, it gives you a lot of visibility into exactly what's in each module. And that means if there's a breaking change in one module, then we would just have to modify the dependent module and just move on with our life. And at that level, of the level of complexity they were working with in those days, it just wasn't that big of a deal. The challenge wasn't keeping a lid on complexity. The real challenge of that era was taking ideas that we had that were this big and putting them into this much hardware. You've got 64 kilobytes, go. And there are people, a couple generations ago, the idea of 64 kilobytes would feel like an absolute luxury. But dynamic linking, that started to change how we thought about this stuff, and how we thought about module interactions. And this is where we started to run into problems with the old approach. We had to think about application programming interfaces as a useful abstraction. When we could split some of the functionality from the main application to some kind of third-party library that we could bring in and link dynamically at runtime, we suddenly wanted something new. We wanted independent evolvability. And so we added this abstraction layer. And the API became an abstraction from the implementation. That way we could start to decouple the actual implementation from the library clients, that we could keep that API layer, that abstraction, stable. And as we changed the implementation under the hood, it wouldn't bleed through. Although decades later, this is still lost on a lot of package developers. The package developers that are like, yeah, this feels small to me. It's a completely breaking change, but it feels small. So I'm just going to call it a point version increase. They don't understand semantic versioning, and it gives us no end of headaches. But what we really want out of this is something new again. We want loose coupling. But all of this was pretty natural in the beginning. Well, I want to call that code over there, so I'm going to call that code over there. I want to call this code over here, so I'm going to call this code over here. It's in the same. It's running across the stack. I don't have to worry about networks or anything else, and it's all visible to me. But then we started building client-server applications, and but what seemed obvious and natural and was right on the tip of our solution space tongue was just calling code the way we'd call code in another method. And we tried to shoehorn the same tightly coupled approach into network-based architectures. And so we started to fully embrace this idea of the remote procedure call, that we would just take a method and just make that method available over the network somehow. It could be over some custom protocol, or DCOM, or Corba, or whatever else. And we would try, but our goal was to try to hide all of that, try to forget that there's a network, and just call code across the wire the same way we'd call code across a local module. And if we didn't need independent evolvability in a normal, tightly coupled client-server application, this mostly works. And of course, by the late 1990s, we started to outgrow this approach, and it's still difficult for developers to change this mindset of local procedure calls to complex, independently evolving distributed systems. And when client-server apps started to increase in complexity to the point where it became difficult to understand the internals of both the client and the server, we had to figure out new ways to work with our growing base of legacy code. So let's see how the old-style client-server RPC scores on our metrics of smart, self-describing, and flexible. Not well. I'm borrowing Mark Richards and Neil Ford's star rating module where 5 is good, 1 is bad. 1 is bad, right? There's nothing really smart there, there's nothing self-describing, and there's nothing flexible. These are so tightly coupled. And in the early days, we didn't even have standards to do RPC. And a lot of people got together and they thought about this, and then the WSDL was born. Yeah. There's always an audible groan when I get to this slide. And then the younger developers in the room are like, what's a WSDL? Yeah, if you don't know, just you're lucky that way. You know, so in the late 90s, early 2000s, a new type of network interaction was born. It was called the Simple Object Access Protocol. So if you look at the history, we had SGML, and that gave birth to XML, and introduced a new standard to describe data that the XML proponents would tell you with a straight face was both human readable and machine readable. Have you ever tried to read an XML document? It was potentially a giant leap forward on the path of at least self-describing APIs, because SOAP APIs are definitely self-describing. WSDL stands for the Web Service Description Language. So it's a bunch of interrelated XML specifications that allow you to describe web services. I never understood why they call them web services, because they apply precisely 0 ideas from the web. But I guess it ran on port 80, so, because that was a big problem with the old ones. Like, what firewall ports do I have to open now? Oh yeah, we let web traffic through. Well, these are web services because they run on port 80. We overloaded port 80. But it never really came to fruition. And in fact, by 2006, 2007, the entire industry just said, nope, no more SOAP. In fact, David Heinemeier Hansen made a statement because they dropped SOAP, Simple Object Access Protocol. Simple. They dropped it from the Rails framework. He says, we feel the SOAP is overly complicated. It's been taken over by the enterprise people. And when that happens, usually nothing good comes of it. And so despite its promise, despite its potential, SOAP never really delivered on the goals of smart, self-describing, flexible APIs. First, SOAP is a verbose and complicated protocol, and you can't really use it effectively without understanding a bunch of interrelated XML specifications. It was slow, and tight coupling was still a problem. In fact, it was even a bigger problem because any kind of independent evolution typically required extensive versioning, maintaining many versions of slightly different SOAP endpoints. And a lot of the practitioners of SOAP fell into the same solution space thinking of trying to make distributed systems work like monolithic systems. So to achieve the goals of smart, flexible, and self-describing, we needed to think beyond just calling functions over the wire. So how did SOAP do? Good on the self-describing. Actually, a couple stars for smart. That was actually one of the neater things. I remember in the early 2000s, in my Visual Studio IDE, I could point my IDE to a WSDL. I'd say, here's my WSDL, it's a URL. Here's my WSDL. And it would read it, and it would generate all of the bindings and everything you needed. So I could very effectively pretend that there's no network call at all. until the network reminded me, which was often. Remember the fallacies of distributed computing, right? The network is reliable, the bandwidth is infinite, all of these things. These are the fallacies because these are the things that we just like walk right into and we ignore until they cannot be ignored. Well, after SOAP, where did Rails and where did everybody go after SOAP and XML and all of that stuff? Well, we sort of kind of went with REST. Now, Roy Fielding derived the REST architectural style in his 2000 dissertation, Architectural Styles in the Design of Network-Based Architectures, Software Architectures. And he described a successful approach to building smart, self-describing, and flexible interactions within a distributed system. And around the same time, JSON started getting some traction, and all of us as developers, we said, you know what, XML, we don't like it. This JSON thing, this is a little bit better. And JSON is definitely friendlier than XML. It's more compact. It's got a few more degrees of flexibility that XML didn't have. Not only that, with the decline of SOAP, we really wanted another 4-letter acronym. And this was a 4-letter acronym connected to a doctoral dissertation. So it even had a veneer of academic credibility. So what is REST? Well, REST is an architecture. It's the architecture of the World Wide Web. It stands for the Representational State Transfer. So we don't call functions, we transfer state through representations of these things we call resources. So as an architectural style, REST extends the client-server network architecture with a bunch of constraints. And that was what the thesis was about. It wasn't about REST. It was about architecture designed by constraint and how constraints can yield architectural characteristics. And then he said, here's an example in chapter 5 and derived REST. And it was a collection of 6 constraints. Now, most of these are out of scope for this talk, but he said if it's just this one constraint, this is the name of the architectural style. If it's these 2, this is a different architectural style. So REST specifically by definition is all of these constraints. And one of the ideas is that a client can interact with a server using only a minimum of out-of-band knowledge. What does that mean? It means that almost everything that I need to interact with this server is available through the API. I don't need to first go read a lot of documentation or look at the source code because the documentation is out of date. Who's got documentation? Oh, wow. Okay, so we're definitely reading the source code. My second question was, is it up to date? But I think, yeah. But so documentation, source code, client libraries, all of these things are out-of-band information that you have to get to be able to interact with this thing. And what he described, you didn't need any of that. So part of this is accomplished by standards, and part of this is accomplished by self-describing interactions. So we have this concept of the resource, and this is how we get that flexibility. The resource is an abstraction. The resource abstracts everything in your code and the implementation and the technology behind it. We just have a resource. And a resource has an identity. So a lot of times when we go and build an API that we're going to call REST, really we're just exposing remote procedure call methods to the network, and we just call it an endpoint. And so we're doing RPC over HTTP, but REST has a slightly different philosophy and a slightly different approach. So a resource has an identity, a URI. So this is a URI. This URI actually identifies me as a resource. Now, if you try to get that URI, you're not going to get me. I'm not going to like materialize in front of you because it turns out that I don't serialize particularly well. But that resource, that URI identifies the resource, and if we want to interact with it, we have the uniform interface of the HTTP methods. And so that gives us a uniform interface. If we want to get a representation, we get. If we want to update that representation, I might do a put or a post or a patch. If I want to delete that resource, I might issue a delete. If I want to just get information about it, I might do a head or an options. I might see what representations are around. And as long as I know the identity of the resource, I can interact with it. So I'll either get back a representation of the resource or a standardized response code. And I don't actually have to know whatever code method retrieves that resource. It's abstracted away. And that's beautiful because it means if you decide you want to change it, you can, but the resource and the HTTP methods remain a stable abstraction and allows me to radically change the implementation of an API without ever breaking the contract or needing to version it. Well, that's great, right? That's that. But what about the data contract? That's a question that comes up as well. Well, I don't know why it's doing that. Well, the data contract is what we call a representation. And so HTTP allows us to ask for different representations. So if I build an API right now and you want a JSON representation of that data, well, you either don't specify an accept header at all, and I'm going to default to JSON, or you say get resource accept application/JSON. Or if you want the XML, you could say accept application/XML. Or if you want an HTTP page about the same resource, accept text/HTML. Or if it's an image, you can ask for the JPEG or the PNG. It's the same picture, they're just different representations of the same thing. And you can also do this with the V1 attributes or the V2 attributes. That means the interface of my API never changes. I can just say accept application JSON plus V1 or plus V2 and get different versions of that JSON representation. Or I can have a mobile client and I want a much smaller representation that is mobile optimized than my desktop client might ask for. Same API, same endpoint, same everything, different representations. And so rather than invoking the methods over the wire, I'm sending representations of the state of that resource back and forth. So that's the basic idea. But most of those ideas are lost. JSON and HTTP stuck. So REST generally, when we're looking backwards, it fell short of the vision. We went right back into the solution-based thinking, and we said, JSON, HTTP, cool. I'm going to build an RPC endpoint with no abstraction, and then I have to version and do all these things. And also, even though you can make self-describing APIs, for the longest time there's been no formal specification for describing these. So there's no standards. Now, Leonard Richardson came up because we have varying levels of REST. Some people do everything that I just talked about. And and Leonard Richardson called that a mature REST implementation. That would be level 3 in his model. Some people didn't use hypermedia, but they used all of the correct request verbs in HTTP and URIs. And in that case, that was level 2. And okay, we just use URIs, that's level 1. And then if you're doing RPC over HTTP, he calls that level 0. He calls that the swamp of POX. So the best REST APIs that you typically see, they're level 2. And this is what level 2 looks like. We've got a lot more flexibility because of the resource abstraction. We've got a fair amount of self-describingness because we have a standard uniform interface with HTTP. And it's somewhat smart. There's some good tooling around it. But there's still much left to be desired. Now, because a lot of what we're doing was falling short, we threw code at the problem because you can use code as a versatile enough tool that you can make it solve just about any problem. And we came up with things like Swagger and OpenAPI. And these made a lot of progress on adding to the smart and self-describing nature of REST APIs. Some REST APIs or REST APIs. Now, solutions-based thinking limited some of the utility of this because most REST APIs are RPC over HTTP, which limits the flexibility. But when we look at REST with OpenAPI, there's so much good tooling. There's so many good capabilities. We've got a 4, a 3, and a 4. I mean, there's more than we can do on the self-describing. There's potentially more of the flexibility in the smart, but this is a really great place to be. And this might be optimal. But at the same time, this might be optimal. It depends on what you need. Now, the whole deal of building content negotiation into your application and coming up with all these different varying representations of a resource that maybe you want expanded nested resources where where I'm pointing to another resource in a JSON payload. Maybe I want to expand that so I don't have to make multiple API calls. Or maybe I want a smaller set of resources for the mobile client, and I don't want to bother making all these different custom representations. Well, this is what Facebook said. They said, why don't we just let the client describe exactly the representation they want? And GraphQL was born. Now, GraphQL, there's a lot of power there. There's a lot of capability there. There are some limitations. One of the key things is, REST is an architecture. REST is the architecture of the web, which means it can scale like the web. But GraphQL is code, and it can be challenging when you want to scale that out, especially in microservices environments, where you've got one GraphQL endpoint that allows you to build these composite representations of resources or objects or whatever that exist across hundreds of microservices. But it's very flexible. You can ask for custom representations. It's got a schema. It makes it a lot more self-describing. The schema has types, and it has a full description of what's available. It doesn't have semantics. It doesn't have all of the things you might want to communicate, but it's fairly self-describing. And it's smart. It's got a type system, a query language, execution semantics, static validation, type introspection. So when we look at GraphQL, we get a really strong set of stars. And even though, clearly, if you're in this session, you can see that I've got a little bit of an affinity for REST. I don't always do REST because it's not always the right architectural choice. And sometimes I love starting with GraphQL, if nothing else, because I let usage help me understand how to design my resources. Because I want the right granularity for my resources, so I don't have to make 100 API calls to render one page. It doesn't have to be like that. But that's not a REST problem, that's a resource modeling problem. And I can just see how clients are using it. It's got great speed to market. I mean, there's a whole lot of other abilities that we're not talking about yet. So this is kind of a cool approach. This is a nice little kind of extension onto some of the ideas of REST and the architecture of REST. Now, Google, on the other hand, they decided to double down on RPC and make it smarter and faster. So gRPC began its life in 2015. You've got something like protobuf, which is very opinionated. It makes it a lot more self-describing. RPC is always going to lack flexibility, but there's a lot in there for evolving and trying to squeeze in more and more non-breaking changes. So in terms of the tooling and the testing and a lot of the capabilities, gRPC might be one of the smartest approaches. But it's also fairly self-describing. We lack flexibility, especially given that changing your client requires recompiling your application typically. And so smart, self-describing, and flexible, we're not fully finding that yet. We're still navigating all of these trade-offs. And this is where the work that's been happening in the linked data space has been really exciting. This is really cool stuff. Basically, it's a way to do practical, effective hypermedia in your JSON, in your representations, where everything links to more information. You've got a term, but it's not just a magic string anymore. If you have a JSON doc and you have a property name title, you either have to look at it and guess, read documentation, or just assume. But linked data allows you to have a link with that term title. So don't know what it means? You can resolve it. And if you look up that link, it's going to give you a standards compliant way to describe what that title means specifically. And that's a really powerful thing. The same with the data. The same with you can be unambiguous about your terms, you can be unambiguous about your data. and your data starts to be able to connect the way web pages on the World Wide Web connect. And so there's a number of principles behind linked data. Just like REST, use URIs as names for things. Not just resources in your API, but use URIs as names for things like terms in your payload. Use URIs as names for things like foreign keys that allow you, when you get something, you have an ID that points to something else. Well, rather than just a 4-digit integer that you have to know the specific way to go and ask for that, you get a URI, and you need that, just go and request that URI. The same way you do on the web. There's a link, you click on the link, you go to the next page, and now you have that information. If somebody looks up a URI, give them useful information, ideally in a standards compliant format, and include links to other URIs so people can describe more things. And so this is where the community had been looking at stuff that had been happening in the RDF space and the linked data space, and they said, this is great, but we hate the serialization. RDXF XML? No. And the community got together and they said, we like JSON. So we created something called JSON LD. And JSON LD is an extension of JSON that's 100% backwards compatible. So you've got a JSON API and JSON clients now. You can turn that into JSON LD, JSON with linked data, without breaking anything. And you could even potentially do this without making any changes to your JSON, which sounds like magic, but it really isn't. It's expressive, it's simple, it's community driven. So here's a fairly verbose example. This is JSON, and JSON is just, people say, well, my data is just JSON. Your data is never just JSON. You always impose external semantics. You always do. Usually it's hard-coded in your application, but you can put it in there. So if JSON is just decontextualized name-value pairs, why don't we just add a context? And in here, what I'm saying is all these terms that we have here, ID, name, gender, URL, image, dress, email, birthday, birthplace, these are all terms in the schema.org vocabulary. And I'm saying that the column I'm calling ID here is actually the identity of the resource, and the resource has a base of w3id.org/people/Michael. And that I have a type, my type is a person, and my address has a type of postal address. And this really came out of a lot of what we do when we build APIs is we just expect every time we need to consume a lot of custom code, every time we need to consume a new API, we need to write a lot of custom code to re-implement, recreate, and redefine these semantics and these rules and all of this stuff. But it turns out there's a company out there that wants to consume your APIs, but isn't going to write any custom code, and that company is Google. They're not going to write any custom code to consume your API unless they have a very, very good reason to. And so most of the time, the answer is no. And so that means that you need to give them data in a standards compliant way. And so Google collaborated with Microsoft and Yahoo and Yandex and a couple other companies, and they defined schema.org as a standards-based vocabulary. And there are all these terms and all these types and all of these things. And now fully half of the indexed web actually contains linked data embedded. That is structured data because this is feeding Google's knowledge graph and feeding a lot of interesting things. Also feeding ChatGPT, which is amazing. That ChatGPT understands all this JSON LD. That's a pretty useful thing. So when we look at level 2 REST with linked data, now we're really getting somewhere because linked data allows all of the data to be self-describing, and most of the interactions are self-describing because they follow the standards. It's smart, it's flexible because you get all of the flexibility of the resource abstraction and everything that REST gives you. But we're still not at 5 stars. Well, what else do we have? Well, we can do more with hypermedia. We do a lot with hypertext, HTML, hypertext markup language. But that's one form of hypermedia. There's all kinds of hypermedias. And if we look at a website, if we go to a website, if we go to like, if we go to wikipedia.com, you're going to get a page, hypertext, hypermedia, with a bunch of links. And it's like, hey, welcome to Wikipedia. Here's all the places you can go from here. Oh, by the way, if you'd like to search Wikipedia, here's how you construct a search. Now, our browser takes those instructions, gives us a box and button, but under the hood, it's just instructions for how to construct a search. You go to a different website, it's got different links that you can go to, it's got different capabilities, but our browser never needs to stop and read documentation, download plugins, or anything like that. It doesn't matter who built it, when it was built, what it's running on, where it is in the world. Because it's fully self-describing, our browser just renders it and makes available all of the capabilities. And we can actually do the same things with our APIs because it's the same architecture, it's the same set of ideas, it's the same set of tools. And so what we need is a standard like HTML, where HTML can tell a browser how to construct a search box so we can search Wikipedia. Well, why can't we have a similar standard for JSON that tells us, hey, here's an API, here's all the things that you can do with it, here's what it's going to expect, here's how to create a new one of these, here's how to get the collection of one of these, here's how to get page 2. And so people have been building hypermedia standards for APIs. We have things like Hydra and HAL and Siren. And this is where we get closest to 5 stars across the board. It doesn't make it a panacea, but I'll talk about that in a moment. And so at the root of hypermedia, it's just adding links to do more. You've got a payload, and it's like, oh, if you want to retrieve Michael's friends, there's the URI to retrieve Michael's friends. But hypermedia says, well, something like Hydra says, well, if we can use linked data to describe the data and the semantics of the data and the rules of the data and the constraints of the data and the expectations of the data, and we can create a vocabulary that does all of that, why can't we create a vocabulary that describes an API and all the things that we can do with it? And this is where I get really excited about Hydra. Hydra's been around for a decade. Marcus Lanthaner, a developer at Google, came up with it. It's on the standards track of the W3C. And as a proof of concept, all of these years ago, Marcus Lanthaner built a generic Hydra client that you could point to any Hydra API and it would generate the front end for it. It wasn't pretty, but that was amazing. A web client for any API. Any API as long as it used the Hydra vocabulary. So you can see this, right? We have a context, we have an ID, we have a type, we have supported operations. I can create a friend, which is a create resource operation. It takes a method of post. It expects a schema person and returns a schema person. And so all of this can be discovered in band to dynamically build an entire API. It might be for me. I am expecting a call. But tell them I'll be done in a few minutes. Now, we're almost there. We are almost there. There are still limitations. One of the things that happens, and I've had this happen to me, is gone into an organization and we have these problems. We want these capabilities. And I say, well, have you heard of Hydra? Have you heard of linked data? And first thing we do is we go out there and say, oh, there's not a lot of tooling out there. I guess we'll build some. And I say, we're going to open source it, right? And the business says, yeah, of course. These are all open standards, open source. We're going to give back. We like to give back. And then they see how powerful this is and what kind of agility this gives the organization and what kind of capabilities that they get right out of the box with this stuff and what kind of possibilities it starts to unlock. And all of a sudden, they say, oh, I don't know if we should open source this tooling on an open standard. This is our secret sauce. This is our competitive advantage. But that is changing. But that's how powerful it is. It's an open standard. It's public, it's open source. But when companies see how powerful it is, they're afraid of what will happen when their competitors have it. But we looked at all of these, and we see, okay, this is the highest scoring of all of them. So is this what you should do? Of course not. What? Oh, thank you. Yeah. It's not the end, but I appreciate it. We look at it, and this is, what did Mark call this? It was the out of context anti-pattern, I think. Is that right? Well, you have this one, but we might also need these. Because, while our REST level 3 with linked data is smart, is self-describing, it's flexible, the speed to market is not great. If you're gonna build one of these vocabularies, that takes time and expertise. If you're gonna build a REST API, you're not just taking your object model and exposing that as your resource model. That's a bad idea. And this is why people get mad at REST, because that's when you have to make 100 calls to paint one page, because our resources are the wrong granularity. We didn't bother to design resources. But designing resources takes time. The abstraction is great. Wonderful abstraction with level 3, but the performance, it's not going to outperform gRPC. And so performance matters most. You've got different options. Tooling is not there. Difficulty, it's a little bit hard to do some of this stuff. Our frameworks are so used to the shortcuts we take when we build REST APIs that the defaults are all of the shortcuts, and you have to bend over backwards to get all these capabilities like content negotiation into your frameworks. But we've got 2 minutes left, and I want to talk about the future a little bit, though. So there's this, there's this quote from Ruben, I forget his last name. He says approximately half of all of the talks at API conferences. That's a real thing. They start with a variation of this slide. We're doing great because now there's more than 12,000 APIs. And Ruben says, personally, I never understood how overgrowth could be a good thing. 12,000 APIs means 12,000 different ways of engaging in machine-to-machine interaction. And even today, I see the same approach in multiple ways of engaging in machine-to-machine interaction inside of a single system. Every custom API is a new standard. More recently, I saw this tweet, that if applications interoperated with a single generic uniform HTTP API, the whole API industry would go away. A data-centric architecture can get us there. And something really interesting is happening with the data-centric space. When he tweeted this, when Martinez tweeted this, there was the usual knee-jerk, well, that's impossible. Despite the fact that these ideas have worked so well over the last 30 years that we don't even think about it. But he says, yes, universally, I agree. But clever enterprises are figuring this out, and those who think long-term will gain competitive advantage. And he's correct. The long-term thinkers are figuring this out, and they're gaining competitive advantage. That being said, in our industry today, 40 years of evolution, the goal of building smart, flexible, self-describing APIs seems elusive. But I would definitely check this out. The Data-Centric Manifesto. This is a new way of thinking of, instead of building silo after silo after silo after silo, then we have to write all of this custom code to integrate, to get new projections, to answer new business questions. There are different ways to approach this. I show this slide, and everybody says, what's the purple thing in the middle on the right? And really, it doesn't matter. It's an abstraction. That it doesn't matter where the data is, because the data moves, the data shifts, and the data can exist independently of applications and application-informed semantics. So we are out of time. Check out datacentricmanifesto.org, because there's some really interesting things going on in that space. And I'll leave you with this question. Why does your API require custom code derived from documentation? Why is it different from a browser? And I think the answer is because the only reason is because we think there's a difference between the web and an API. So with that, the decisions that we make, they're going to not only drive the current capabilities of our system, but they're going to massively inform future capabilities like knowledge graphs, like the API, like the data-centric stuff. And if smart, self-describing, and flexible are key architectural drivers, there's massive potential in systems that adopt these ideas. Thank you.